nanohub.org.
Online simulation and more for nanotechnology.
Now let me just remind you what we're talking about. So we have covered basic probability theory. We have covered how you can quantify your uncertainty about some quantities, some parameters of your models, and we have talked about parameters that could be functions, right? So that was the Gaussian process stuff we talked about. We discussed how you can reduce the dimensionality of a Gaussian process, etc., etc. And then we moved to Monte Carlo, and we moved to Monte Carlo in order to study the first real problem, which was the uncertainty propagation problem. Okay? So let me just remind you what the uncertainty propagation problem is. You have a model, it's your model, okay? Whatever you're doing, it's a physical model that you're interested in. And you have already quantified the uncertainty of some of the inputs of that model, and what you want to do is propagate this uncertainty through your model to any quantities of interest you may have. Okay, so this is the uncertainty propagation problem. And we already learned about two ways you can use to solve the uncertainty propagation problem. One way is to just sample the hell out of it. You sample from your inputs, you evaluate your model, you look at your outputs, you repeat it 10,000 times, and you do histograms of whatever you want, okay? And we discussed Monte Carlo techniques based on random numbers, and we discussed also techniques based on Latin hypercube designs, which behaved a little bit better. So that was what we covered last week in 2 lectures. On Tuesday, we talked about another technique that allows you to propagate uncertainties with just one sample, with just one evaluation, okay? And that was based on approximating your model with a Taylor expansion. So you took your model and you said, let's assume it is linear, okay? Let's just linearize the hell out of it. And evaluate it at the maximum, the most probable input, okay? So that's one thing that we need to do. And the other thing that we needed to get is the derivative of your model at that particular point, okay? And we call this technique the perturbative technique. Anyway, it is not very accurate, but it costs nothing. And it is perhaps the first thing you should do as soon as you can calculate the derivative. And we talked about, we said that getting the derivative may be challenging if your model is a differential equation or a partial differential equation, and then you would need the method of adjoints. I already talked about it for like 5 minutes, so I don't expect you to really understand how the method of adjoints worked. But you know the name of that method, and trust me, it would take you 1 afternoon to really understand what it does if you want to use it, okay? The method of adjoints just gives you an ability to calculate the derivative of the response of a dynamical system with respect to any parameter you may have, or the derivative of the solution of a partial differential equation with respect to any parameter you may have, okay? And you can use this derivative to build the perturbative approximation to uncertainty propagation. Anyway, that's what we covered last time. Today we're going to talk about another uncertainty propagation method called polynomial chaos. It is the most popular uncertainty propagation method, and even though it is approximate, it can be made as accurate as you want, okay? And there are 2 flavors of polynomial chaos uncertainty propagation. One is called intrusive, and the other one is called non-intrusive. Today we're not going to talk about any of them, okay? Today we're just going to talk about the polynomials. Next time I'll talk about the intrusive uncertainty propagation method. Today I'll just show you what it can do, but I will not really tell you how it can do it. I will tell you that on Tuesday. Anyway, polynomial chaos is based on the idea that you take your model, your physical model, and you expand it in a polynomial basis. Okay. Now, how you do that? There's two ways to do that. You can either evaluate your model at a finite number of times. You can see x and y's and try to come up with a polynomial expansion based on examples of inputs and outputs of your model. This is called the non-intrusive way. It just uses whatever solver you may have for your model. And the intrusive way involves writing equations for the polynomial coefficients themselves. Okay? So basically it involves going and changing, writing a solver from scratch, a solver that automatically propagates uncertainties. So we're going to do that on Tuesday because it is a little bit involved. And we're going to do the non-intrusive methodology on Thursday. Today we'll just talk about the polynomials, okay? So remember that the idea is to take your model and expand it on a polynomial basis. Now these polynomials are special polynomials. They are orthogonal polynomials with respect to something, okay? So I'll have to tell you some things about the math behind this, okay? Don't be scared. You will learn about, I'm sure you have heard in the past about Hilbert spaces, Banach spaces, etc., norms, metrics, inner products. I will tell you all about that in like 30 minutes, okay? Usually takes a semester of a real analysis class. So you're not really learn anything but the names. I'll show you that you already know things that look like Hilbert spaces. The standard Euclidean space is a Hilbert space, and all Hilbert spaces look like the Euclidean space, like Rn. They all look the same, okay? And I'll try to make connections like that. Okay, the reason I'm going to do that is to demystify some of the things about orthogonal polynomials, polynomial chaos. Actually, it is much easier than it looks like if you don't know these things. So I will define Hilbert spaces. It will take me a while, like 10 minutes, okay, but it's not a big deal. Then as soon as I have Hilbert spaces and I have told you about orthonormal basis on Hilbert spaces, which is basically, you know, the standard basis of Rn, these EIs that we're using all the time. So I will tell you there are EIs in general Hilbert space, and I will tell you how they look like. And now once we have done that, I will introduce a specific basis on a Hilbert space, which is a polynomial basis, okay? And this is basically the definition, it's going to be the definition of the orthogonal polynomials. And then I will show you some of these orthogonal polynomials in one dimension. I will tell you how you can put them together in more than one dimension. When you have, by dimensional now, I mean the dimensionality of the input to these polynomials. And then I'll show you some basic properties of them. Okay, so it's a lot of math, but I think it pays off to see it once, okay, and to demystify it. So first, let's talk about the vector space of square integrable functions. And you should think of this as the space in which your model lives. So let's introduce a random variable x, which is all the uncertain parameters of whatever you're studying, right? And this comes with a probability density p of x. Okay, so we introduce these things, the random variable that corresponds to all our uncertain inputs, and a probability density on that random variable. And we define this nice space of functions, which is the space of functions that have a finite variance under this probability density. Okay, they're called p-square integrable. So that this expectation right here, the expectation of the square, exists. Okay, all these functions, if an f of x here is a quantity of interest for you, all we say is that this quantity of interest has a finite variance. Okay, so it's a very, simple restriction. We just say we don't want to have to deal with things that if we square them, we cannot integrate them. That's all. All right. So this is a very nice space. It's basically a set of functions. All right. And your model is probably one point in that space. And it is a vector space. Remember what a vector space is from algebra? A vector space is a space that satisfies the following properties. If you take two elements in this space and you add them together, you get another element in that space. So you can take two functions, add them together, the result is going to be square integrable. And the other property that the vector space should satisfy is if you take one point in that space and you multiply it with a real number, you will also get a point in that space. So if you take a function, you multiply it by 10, you will still get a square integrable function. No big deal, okay? So the space is the space is a vector space if it is closed under, let's say, addition and multiplication with scalars. That's pretty much it. So, do you know of any vector space? Of course. This is one, okay? But the very common one is Rn with a common summation of vectors and multiplication of vectors with scalars. This is the standard vector space. This is a generalization of that. All right. Now a vector space is called an inner product space if it has an inner product. An inner product is basically a generalization of the dot product in Rn. Remember that in Rn we had a vector and we can dot it with another vector and get a scalar. Same thing, you can do it with functions. So we are going to define here a product, okay, that takes two functions and returns a scalar. We're not going to call it dot product, we're going to call it an inner product, but it's just a function, and the function is defined like this. So it is, we're going to use this shortcut notation, angle f, comma g, right angle, and we're going to read the inner product of f with g. You can also say the dot product. So it is defined to be this expectation, the expectation of f of x times g of x, the expectation of the product of the two functions. It's just defined to be that. Now this has exactly the same properties that the dot product has in Rn. Exactly the same properties. It is indistinguishable from the dot product actually. And what are these properties? Well, first of all, if you plug f twice in this function, you get a positive number, okay? If you take a vector x and you dot it with itself, you get a positive number. It is symmetric. F dot g equals g dot f. Big deal. I mean that, it comes from the definition because it is just an integral. It is linear. If you multiply a function with a scalar, then the scalar just comes out. Okay, and this is also trivial to show. It is also linear in the function itself. So if you take the dot product of f with g plus h, then that's the dot product of f with g plus the dot product of f with h. It's exactly the same properties that the dot product in Rn satisfies. Exactly the same. No difference. The only difference is that these things are functions. Apart from that, the properties are exactly the same. Any questions about this? Okay. So, if you have a vector space with an inner product, then you call it an inner product space. And why is an inner product space important? Well, if you want to define convergence of functions, you can do it using the dot product. Because convergence requires the definition of a metric, and if you have a dot product, you can get a metric. A metric is just the distance between two points in the vector space. And how do you get a distance? Well, if you have an inner product, you can define a norm, and I will define it for you in a while. And if you have a norm, you can define a metric. So once you have an inner product, you can define a metric, and you can talk about convergence of sequences of things. Okay? and so on. So let me show you what a norm, what is the norm you can define with this dot product. Here it is. Okay, so you define the norm of a square integrable function to be the square root of the dot product of f with itself, and it's this thing. Do you notice the resemblance with the definition of the Euclidean norm in Rn? It's exactly the same thing, with the exception that the integral has now become the summation has now become an integral, and we have introduced these weighting factors. Apart from that, it's exactly the same, right? So let me just write it down for you so that you can remember it. To notice the correspondence. So if you had a vector, right, in the Euclidean space, then the norm of that vector is defined to be the sum of the squares 1/2. You see, it's the same thing. The summation becomes an integral, and we just weight everything with something, no big deal. All right? So this function is a norm because it satisfies exactly the same things, it has exactly the same properties as the standard norm of Euclidean spaces. So first, it is positive, okay? Second, if it is 0, then the function is 0, okay? If the norm of x is 0, then x is 0. The sum of the squares of all the components is 0, therefore x itself should be 0. What else? It satisfies this property. It's kind of linear. So if you multiply your function with a number, that number comes out of the norm, but you have to put an absolute value there. Okay, and that's pretty much it. These are the properties of the norm. And yes, I forgot to say that, but the norm actually measures how big the function is, the magnitude of the function. If the function was a vector, an actual vector, it will measure the length of that vector, right? But it's a generalization of that concept. Questions? Okay, now let's define a distance. So a distance is basically a function that takes two inputs, two vectors, and it tells you how far apart they are. That's all it does. Okay? So how can you define a distance with a norm? Here's how you can define a distance with a norm. You can say that the distance between f and g is just the norm of their difference. Right? Because f and g are in the same vector space, their difference is going to be in the same vector space, so you're allowed to write that. Okay, that's how you define it. And if you look at what this was, it was this thing. Okay? It's the difference of f of x minus g of x squared integrated over the possible p's. I have forgot over the density. All right, and this is a distance metric because it satisfies exactly the properties of distance in Rn, and these are basically these. The distance between any 2 points is positive, obviously. The other property is that if the distance between two things is 0, then we're talking about the same thing. And it is symmetric. The distance between g and f is the same as the distance between f and g. Makes sense. And the final property is the trigonometric inequality. So you need to think of a triangle here. So if you think of this as f and this as g, this would be f plus g. Anyway, let's not even talk about it. It's the trigonometric inequality generalized. I will confuse you more. Anyway.
Here, f and g are values, right? And
Functions.
functional values.
Functions. So all these are functions of functions. So a point in the vectors, original vector space that I introduced A point in that vector space is a function. Okay? And now we're defining the magnitude of a function. We're defining the distance between two functions. And we are defining the dot product between two functions. Okay? Alright guys, so let's move to the next part. So we have now we have a vector space with a metric, okay? And we're going to define the concept of a Cauchy sequence. Sounds a little bit weird, but it's actually very easy to understand what it does. So a Cauchy sequence is basically a sequence of functions, f1, f2, f3, which could be, for example, the result of approximating your model with polynomials of different degree, and you start increasing the polynomial degree, okay? So this would be a sequence of elements. And this sequence of elements looks like it converges, okay? What do I mean by looks like it converges? I mean that consecutive terms come closer and closer together. All right, that's what I mean. So if you go far away in the sequence and you compare, I don't know, fn to fn plus 1, the distance between them goes to 0. Now it just happens that not all sequences that satisfy this property converge, in all spaces at least, okay? But if a sequence satisfies that property, if a sequence looks like it converges, then we're going to call it a Cauchy sequence, or a basic sequence. But the mathematical definition is like this. This is correct, okay? And it basically says that if you pick any small number epsilon, and you can go far away in the sequence, and the functions will start being closer than epsilon together. That's all it means. All right. Now, the Cauchy sequences look like they converge, and this is pretty much if you construct an algorithm that approximates something. This is the only thing you can actually test, right? You can test whether let's say your function satisfies this property at consecutive iterations. But not all these sequences converge in all vector spaces. And if they converge, so if the Cauchy sequences, the sequences that look like they converge, do converge to an element in the vector space, then that vector space is called a complete vector space. So, in other words, a metric space is going to be complete if all sequences that look like they converge do converge to a point in the space. Okay? Now, in the Euclidean space, with the standard dot product, all sequences that look like they converge do converge to a point in the space. And now the same thing happens to the space of square integrable functions. Okay, all the sequences that look like they converge, they will converge to a square integrable function. Anyway, before we get there, just some names. So a vector space with a norm that is complete is called a Banach space. If it's green, it's called a banana space. And in our case, the space of square integrable functions with this norm is a Banach space, okay? And a Hilbert space is just a vector space with an inner product that is complete, okay? A vector space with an inner product in which sequences that look like they converge do converge to a point in the space. In our case, the space of square integrable functions with this inner product, which is just the integral between two functions, is a Hilbert space. Okay? So why do we care? We care because as soon as you realize that this is a Hilbert space, this means that all the theorems that you have for Rn all of them, they are satisfied for this space. You don't even have to prove them again. They just hold. Okay? Can you define orthogonality between two vectors in Rn? You can define orthogonality between two functions. Do you have formulas that will tell you how to expand a vector in Rn in an arbitrary basis? The same formulas hold for expanding a vector in this function space in an arbitrary basis. Can you define an orthogonal basis in Rn? How do you do it? In the same way you can do it here. You have the Gram-Schmidt procedure that tells you how to take a set of linearly independent functions and turn them into an orthogonal basis. The same procedure, the Gram-Schmidt procedure, holds for functions. Okay, that's why you do all that math. And you could either realize that you're talking about the same object mathematically, or you can just prove everything from scratch with this thing. It's your choice. Okay? Anyway, so why Hilbert spaces? We can define orthogonality, normalization, convergence. We can define the concept of orthonormal basis. We can construct orthonormal basis using the Gram-Schmidt procedure, which you should have learned in linear algebra, etc. All right, so here's the concept of an orthonormal basis for our particular problem. So a sequence of functions, phi1, phi2, is said to be an orthonormal basis if three properties are satisfied. One, this should have been phi instead of f, okay? Phi I and phi j is 0 whenever I and j are different than okay? So any two functions are orthogonal, okay? So this is like saying E1 is orthogonal to E2 in Rn. The other property is that each one of the phis has a norm equal to 1. The magnitude is 1. And then any element of the space can be written like this. Okay? Like a linear combination of the bases you have. Now in Rn, you would stop at n. Here you have to go to infinity, because you have an infinite number of basis functions in this function space. Any questions? So do you know of these things? Yes, you do. You just have to replace this concept with a concept you already know, right? So this is one thing that you should remember from standard calculus, okay? And then you can take any vector and expand it in that standard basis. And you see it's the same formula. Just a generalization of these e's. Remember the e's, right? I'll just write them like that. Vectors, standard vectors.
So instead of vectors, we have functions here.
Yes, the functions are the vectors. Okay? That's the leap we did. Anyway, and for convenience, we're going to be writing, again, I remind you that this is a type of phi I, phi j. We will be writing that the dot product between phi I and phi j is the Kronecker delta. This will simplify things a little bit. And the Kronecker delta is 0 if I and j are different and 1 otherwise. Okay, so this tells you that the basis is orthonormal. Okay, now how do you expand a vector in an orthonormal basis? So you take any function, and as soon as you have an orthonormal basis, you can write it like that. You can write it as a linear combination of the basis functions. And one way to get the coefficients is to do this dot product. So the coefficient of the basis function phi j is the projection of the function on phi j. Just like the coefficient of a vector in a specific direction comes by the dot product of the vector in that with a unit vector that points in that direction. It's the same thing. Okay? So how can you prove this? It is nice to show it once. Okay, so all you have to do is plug in there the expansion and use the property of the inner product, the linear properties of the inner product, to take the summation outside, NCI outside. So you got phi I, phi j, right? And this phi I, phi j is either 0 or 1. It is 0 if I and j are different, and it is 1 otherwise. So it is that Kronecker delta. So this is just gonna give you Cj. This is the only term that is going to survive. And this easy to show it. Yes?
How do you change the limit, change the order of the limit and the inner product?
The order of what?
Taking the limit.
Did I take the sum outside?
Yes.
So you take the sum outside because the inner product is a linear function.
It is an infinite sum.
Yes, it is also a continuous function. So you can exchange the limit. There's no problem. Okay? So your problem is that this is limit, okay, etc. Don't worry about that. We will need the semester to explain that. Okay? But the function, when you think of it as a function of whatever is inside, well, of the c's, for example, it's going to be a continuous function of c's, so you can actually take the limit out. There's no problem. Okay? It's a very nice function. What was that?
But it's a discrete sum.
There's no problem. I'm not going to worry about the infinite summation. You can take it out, no problem. Okay? We're not going to be paranoid with nuances. If you don't like taking it out, if it is an infinite thing, taking it out finite, fine. Just throw away some terms. Okay, I'll tell you, there's absolutely no problem. But other questions, yes.
So the phis and the f's are functions that we define according to the problem that we have, or how do we find them?
So typically, I'll tell you this in the next slide, but these phis are a basis, okay, that comes from this guy. So it's an orthonormal basis. It's orthonormal with respect to this p of x. And this p of x comes from your problem, okay? And this f is basically your model. And you want to take your model and expand it in this basis. And one way, if you could do this integral, then you could expand your model in this basis. But you can actually do it in other ways as well.
So it's not enough just to have data as in the homework with the excited.
You could do it with just data. So there are actually 3 ways to do it. One way to do this expansion is to have data of x and f of x and try to come up with the coefficients. That's one way. You can just do regression, just like we did. Another way is to try to evaluate these integrals somehow, okay, directly from these integrals. This would be called the Galerkin approach. And there is one more way, which is to take this expansion and plug it into whatever equation you have and derive an equation for the coefficients, which would be the intrusive approach. We will do both, all 3 approaches, but one at each lecture. Right now, I just want to talk about the phis, okay? Anyway, there's one more formula that I want to prove. I'm doing the engineering proofs, guys, okay? So I don't have to worry about that infinity there. I can take it out of expectations, put it back in, right? Because otherwise, honestly, it is not, if it doesn't hold, I will not do it, okay? And if we worry too much about it, it will take us 3 years to understand this concept, okay? But we don't need it to understand the concept. All right, so this formula is called Parseval's formula, and it gives you the norm of that function. So it tells you that if you have this expansion in this basis, then the norm of the function is the norm squared is the sum of the squares of the coefficients. So this is exactly the same formula that you have in Rn. In Rn, if you have a function, a vector, and I ask you what is the norm of that vector, you're going to say the square root of the sum of the squares. Well, here it is. The square root of the sum of the squares. All right, how do we know that? How can we prove it? Well, we start by the definition of the norm. The definition of the norm is basically that it is the square root of the inner product of f with itself, right? And then you replace f with the expansion. I'm using a different index at the two summations so that I don't mix things up. Okay, the inner product is linear with respect to both summations, so you can take both of them out. Ci, Cj, phi, Fj. But phi and Fj are orthogonal, so you're going to get either 0 or 1. So delta Ij. Okay, and the only thing that's going to survive is the diagonal terms. So you will get sigma I Ci squared. That's all. Okay? Fairly simple. All right. Let's look now at some specific examples. This is all general. Okay, so any square integrable, any space of square integrable functions. So let's now go to scalar square integrable functions. Let's derive a specific set of orthonormal basis functions called one-dimensional orthogonal polynomials. Okay, so first of all, this is how a polynomial looks like. Okay, everybody agrees on that. Constant terms, linear term, quadratic term, cubic term, etc., up to a specific degree. So this row here is called the degree of the polynomial, and it can be whatever you want. Okay. Now the space of scalar square integrable functions is this. Right? It's just functions from R to R. The input is a scalar. That's all I'm talking about. And a set of orthonormal polynomials is a set of polynomials. Okay, so it's a set of functions, phi1, phi2, that satisfies the following properties. First of all, each one of these functions is a polynomial. Okay? Otherwise, I would not be calling it a set of orthonormal polynomials. I would be calling it a set of whatever. Okay? The other property that these guys should satisfy is that they should all be orthogonal to each other. So if you take the inner product of phi with phi you should get 0. But this is the inner product we understand. Okay, this integral. And the other property is this is the normal part, is that the norm of these functions is 1. Okay? So if you can and you see that the construction actually depends on p of x, right? So this is what defines these polynomials. So as soon as you have a p of x in your problem, you can define these polynomials. Okay? And this should satisfy this property. It should be polynomials, orthogonal, and normalized. That's all.
So you're saying from these equations we can derive phi?
Yes. So all I'm saying is that if somebody gives you a p of x, it is entirely possible to come up with these phis. Okay, to come up with a basis for the space of square integrable functions that is polynomials. Okay, it is also possible to construct a basis that is made out of sines and cosines. That will be a Fourier basis. It is also possible to construct other types of bases, like a wavelet basis, whatever. Okay, but if you want it to be polynomials, you would call it orthogonal polynomials. How do you construct orthogonal polynomials? You can use the Gram-Schmidt procedure of linear algebra, because it is as if we are in Rn. It's exactly the same thing. So you can start with a set of linearly independent vectors, like 1, the constant polynomial, and then a linear function like x on its own, and then x squared and x cubed. All these things They are all linearly independent when you think of them as functions. And then you think of them as vectors in the Hilbert space, and you use the Gram-Schmidt orthogonalization procedure. What is that? Google it, remember it, okay? It's not a big deal. It's a way to get a set of linearly independent vectors and turn them into a set of orthogonal vectors. Okay, this is what it does. Anyway, you could do that. You could start from the monomials and orthogonalize them. No problem. This is not very stable. Gram-Schmidt is not very stable. And you should not really do it unless somebody forces you to do it for some whatever reason. There are efficient ways of constructing these polynomials, and there's actually code that you can use to construct them automatically. As soon as you have a P of X, you can get these polynomials. And some of these algorithms are described in this paper by Gao-Chi, who's a professor here at Purdue in computer science department. And it's called OrthPol. So this guy wrote in 1994 a package in Fortran that allows you to evaluate, to construct any orthogonal polynomial you want in one dimension. Okay, and I wrote a Python interface for that Fortran code so that you don't even have to deal with the Python with a Fortran code. And you will see the handout how easy it is to construct the polynomials as soon as you have a P of X. Okay, so here's some examples of these polynomials. So if X is a standard normal, then these are the orthogonal polynomials. They're called the Hermite polynomials. Okay, so the first one is the constant, then it is a linear, then the quadratic one looks like that. Well, why does it have this -1? Because if it didn't have it, it would not be orthogonal to this and that. Okay, that's why. The fourth one looks like this. Again, it's not just x cubed, it needs something to become orthogonal to everything before it, and so on and so forth. Okay, and these have a specific name, and they're called the Hermite polynomials, and you can actually get them with Gram-Schmidt procedure, but don't do it. Okay, so this is P of X, and this is how they look like. Okay, they're polynomials. Okay, that's how they look like. The blue one is the constant one. The second one is the orange one, and then the fourth one, or the quadratic one, is the green one, the cubic one is the red one, and so on. All right. If you use an exponential density, so if P of X is the probability density of an exponential random variable with rate 1, then these are the polynomials you get, okay? And these are called the Laguerre polynomials. Do you have to know the names? Of course not. Okay, I don't even know the names. I have to look at them and tell you what they are. But they have a name. They're called the Laguerre polynomials. So this is the probability density that, corresponds to the Laguerre polynomials. A probability density that puts weight only on positive x's. It is 0 here. So the polynomials are not even defined in that space. It doesn't matter what they are. And here's how they look like.
P of X is C times the phi, right? P is C times phi, the linear combination of C and phi.
P of X here,
Yeah, P of X.
Is the probability density.
Yeah, is C of C times
It is
phi.
just this.
Yeah. The linear combination of C and phi, should give me e power minus x.
So the linear combination of what?
Some constant times the basis functions should give me e power minus x. Is that
I'm not sure I understand what you're talking about.
so? E power minus x is equal to sigma times C times phi. Some constant times these basis functions.
No, what happens here is that the following relations hold. the linear product of phi I and phi j, this, okay, which is defined by 0 to infinity phi I x, phi j x, p of x, which just here happens to be this. This is delta ij. So from here I can read that 0 to infinity of 1 times minus x plus 1 e minus x dx is 0, etc. Okay? The plots do not look, the names do not look right. Do they? Let me see. 1 minus x plus 1. Yes, they don't look right, but it shouldn't matter because you can just multiply that with a minus sign and it's the same vector. Okay, it's the same vector. It just points in a different direction, but you can still use it as a basis. Okay, there's no problem. I mean, there's no right-hand side rule here, you know, that makes the order of the vectors important. Because we're not going to take cross products, so it doesn't really matter where they point. Okay, what matters is the direction. All right, so they look like that. These are the Laguerre. Let's go with one more. If the probability density is uniform, then the name is Legendre polynomials. Okay, and they look like this is what they are, and this is how they look like. Okay, so the probability density here is uniform between -1 and 1. Okay, but using Gauss's code, you can actually go and do more complicated stuff. So you can take, for example, a probability density that is a mixture of two Gaussians. So with probability pi1 this Gaussian and with probability pi2 this Gaussian. So this is a probability density that looks like this for some specific values of pi1, mu1, sigma1 and so on. So it has two bumps and it is absolutely possible to define orthogonal polynomials for this. And they look like that. Okay, so in the handout you will see how you can do that using Gauss's code. And of course, if you had samples of x and you did a histogram of x, then you could use that histogram to define orthogonal polynomials as well. Okay, so as soon as you can estimate the density of x, you can define these polynomials. Anyway, in higher dimensions, it is a little bit more complicated. Polynomials in higher dimensions, they look like that. Okay, so some coefficients times something that involves all the dimensions of x raised to a given power. Okay, sum over all the possible combinations of powers. Okay, I mean it could be 1 and then x1 plus x2 and then plus x1 times x2 and etc. etc. Okay. Now the space of square integrable functions is this. This is the one we started with. And again, a set of orthogonal polynomials satisfies the following properties. Each one of these elements must be a polynomial and each one must be orthogonal to each other and they all should all have norm equal to 1. And again, the Gram-Schmidt process still works. You can just come up with all the possible monomials, put them together and use Gram-Schmidt to orthogonalize them. But there is a special thing you can do. If, for example, your random vector, consider each one of the components, x1 up to xd of your random vector, and if each one of your random variables is independent, if each component is independent, then the probability density is going to factorize like that, okay? And then what you can do is you can build the orthogonal polynomials of each one of the components and then put them back together. Alright, so for example, you build orthogonal polynomials for the first component, for the second component, for the third component, and then you can build multidimensional polynomials by multiplying the components to each other. Okay? So this is called a tensor product between sets of functions. But who cares? You just take the product of all the different polynomials and you can pick one polynomial from each dimension and make all possible combinations. Okay? And I'll show you how it works. So here I take a random vector that is basically consists of two independent random variables, a normal and an exponential. I build the orthogonal polynomials for the normal. I build the orthogonal polynomials for the exponential. So I have the Hermite and the Laguerre. And I take all pairwise combinations of these two. And of course the first one is just a constant, right? It's the constant of the Hermite times the constant of the Laguerre. The second one is linear in the Hermite. So it's the constant of the linear of the Hermite times the constant of the Laguerre. The second one is the other way around. It's the constant of the Hermite times the linear of the Laguerre. This one, it's that one over there, whatever it is, okay, and you can just multiply them. You see you have 5, how many you get? 5 times 5, 25, okay? All right, so why do we do all that? I should have probably said that at the beginning, but here's how we do it, okay? We do it for doing uncertainty propagation. So let x be the random vector in your problem, whatever that is, okay? And p of x, the density that you have. And we're going to assume that your physical model is square integrable. So it is inside this space. There's a point in that space, okay? That's all I'm assuming. And now let's assume that somehow you have managed to expand your model, which is f, in this basis. If it is inside that space, it can be approximated. It is exactly like that. Okay? And let's say that you constructed that somehow. There are 3 ways to construct this, but let's say you have done it. Okay? Then the expectation of f of x, so the expectation of a quantity of interest that depends on your model, is just the first coefficient. How? The first polynomial is always the constant polynomial, right? So the first polynomial, let's prove this. Doesn't work. So the first polynomial is always the constant polynomial. So if you put here 1, this becomes the expectation of f. Because this is the definition of this is the expectation of f times phi1. If phi1 is 1, then you get the expectation of f alone. That's all. Do I have the proof? No. But anyway, the first one picks the expectation. And then the variance, which is something else that you may want, is the sum of the squares of all the terms except the first one. I'll show you this, okay? But this is why we do it. Because it is so simple to calculate these statistics. And if you wanted something more weirder than this, like the skewness or whatever, there's still a formula for that you can actually do it, you use just with the coefficients. Okay, so here's the expectation, right? So the expectation of your quantity of interest is the expectation over p of f of x. But look at that, you can just put there and multiply with 1, right? So now it becomes the inner product of f with 1, but 1 is always the first polynomial we have. So C1. Okay, for the variance. For the variance you have this formula, and you already know that this is just C1. Okay, so you have to find this. But this comes from Parseval's formula. So the expectation of the square of your quantity of interest is the expectation of the function squared, which is the norm of the function, which is just the sum of all the coefficients, all right, from the beginning to infinity. And from this, you're going to subtract C1 squared. So you're going to get rid of the first coefficient. This is all. Okay? So once you have constructed it, it is trivial to get the statistics from it. Okay, you just read it from, yes?
Following the methods for constructing the basis function, do we always get a unique basis or?
Yes. Yeah, this is a good question. So the basis is going to be unique up to a multiplicative factor that is minus 1. So it could be, the only difference is that the function could be pointing in one way or the other way, but the direction is unique. So it doesn't really matter. It's as if I'm telling you, you know, you can use in R2, you can use 1, 0 as your first basis vector, but you could also use minus 1, 0.
But if all of the, when you started constructing with monomials,
Yes.
in all of them you have the first term 1.
Yeah, you have to order them according to the degree. Okay, so I see the point. If you are, if you start with the monomials and you construct with Gram-Schmidt, you're gonna get a unique sequence, okay, that may have an arbitrary minus sign, but then you could take that and rotate it, because you can also define rotations in this space. But why would you do that? Because then, you know, once you rotate it, then everything will be of the highest possible of a degree different than, I mean, they're not going to be ordered according to degree. So you wouldn't really do that. Anyway, obviously, this is something I'm going to do next time. Okay, so just to give you an idea of how it works, how you can use polynomial, orthogonal polynomials. By the way, let me tell you something. I kept calling them orthogonal polynomials, but in the literature they're called polynomial cows. This is just a weird name that has stuck. Okay, it doesn't make sense to call them. I mean, in my opinion, the cows term doesn't really contribute anything. They're just orthogonal polynomials. Okay. So you will hear people talking about polynomial cows, and you should just think that they're talking about orthogonal polynomials. It just sounds sexier to call it polynomial cows than orthogonal polynomials, but they're just that, okay? I'm still trying to figure out who came up with a name. Who? Don't be no, he popularized it, but the name is older. The name is at least 100 years old. But anyway, okay, so here's one example of what you can do. All right, so let's take the dynamical system through which we propagated uncertainties the other time. So we have the rate and the initial conditions being random numbers, and they're both standard normal. And what you do is you take the solution and you expand it in these polynomials. Okay, but now the polynomials are a function of the random variables, so the coefficients are functions of time. You have a different coefficient at every time. So if you take this and you plug it into the differential equation, you're gonna get, we'll see that next time, you get a differential equation for the coefficients. Okay, so you get a differential equation for the coefficients. If you take this and you plug it into the initial conditions, you will get initial conditions for the coefficients. And this is what they are for this particular problem, and we will explain that next time. But once you have this dynamical system, you can solve for the you can solve for the coefficients as functions of time, and then once you have the coefficients, you can estimate the expectation of the dynamical system. It's just going to be the first coefficient. You can estimate the variance, which is going to be the sum of the squares of all the coefficients, so on and so forth. And in this way, you can propagate uncertainties efficiently, in this problem in particular. So for example here, the solid curves are Latin hypercube estimated uncertainties, the mean and the variance, okay, with 10,000 Latin hypercube samples. And the dashed lines are the mean and the variance with a polynomial chaos or an orthogonal polynomial approximation with rho equals 1 with degree 1. So just the linear term, okay? And you see that you have, so in this, you're solving a dynamical system, the original dynamical system 10,000 times. In this, you're solving another dynamical system once, okay? This is the difference between the two approaches. We'll explain it next time. So for polynomial degree 1, you see that the mean is matched perfectly, but the variance is underestimated. But if you start increasing the polynomial degree, you take it up to 2, for example, it looks better. And for even higher degree, it looks perfect. Yes?
Does that also save us time and computational?
Yes. So polynomial chaos works extremely well when the dimensionality of the random variables is small, like 3, 4, 5 variables. Then this is what you should use. But you have to pay the price of doing a little bit of math to derive this new dynamical system. But as soon as you have start having, so and in let's say when everything is nice and smooth and you have a small number of random variables, it works. But when you start increasing the number of random variables, because the number of polynomials you need grows exponentially. Because you would construct a set of polynomial bases for each one of the random variables, and then you will take all products between them, and it just blows up. Okay? So there is a hard limit on how far you can go with polynomials. So 10 dimensions, I will bring that table next time. I will tell you how the number of polynomial grows with dimensions. It grows very fast. What else? That's one thing. The other thing with the polynomials is that they don't behave very well when your response has discontinuities. So for example, if you have a dynamical system that passes through a bifurcation point, as you change a parameter, that is going to lead to a discontinuity or a kink in your response. And this cannot be captured with polynomials, because polynomials, they cannot capture discontinuities. They'll give you weird things around the discontinuity. So that would be one problem. And then the other problem that you may have, so high dimensions discontinuities cannot be done. The other problem that you may have is uncertainties that grow fast. So when you have uncertainties that grow, then you can also not use them. So for example, you change exponential decay to exponential growth, even though it seems like a very simple problem and you can actually find the solution analytically, you will need an extremely large polynomial degree to capture the growth of uncertainty accurately, for big times at least, okay? So unless you have a system that goes to a steady state after a while, you should not trust this too much for dynamical systems. Now, what I did for dynamical systems, you can actually do it for partial differential equations as well. Yes.
How do we check the convergence of the polynomial terms?
Yeah. So
Make sure we have enough coefficients.
You do this. Okay. So you you solve the problem for increasing polynomial degrees, And when you see the results being close together, the two consecutive degrees being close together, you stop. Because you know that you have a Cauchy sequence, and in this space, because it's a Hilbert space, it is guaranteed to converge. Yes?
I mean, the point of doing this is basically reducing the number of simulations,
Yes.
the number of evaluations
Yeah.
needed. So what's the point then? If we
Well, you will start with a polynomial degree that you think is enough, 5, and then you will go to 6. Okay, and if you see things changing, you will go to 7. And if things stop changing, you will stop. Otherwise, you will go to 8. And in some problems, they will not stop changing unless you go to 100. And then you cannot solve that problem with polynomial chaos. So the other thing, the other advantage of polynomial chaos versus sampling is that at the end it will give you the solution as a function of the random variables. So once you construct them, you can evaluate the response at any point you want. Because look at that. As soon as you have the coefficients, because you expand the response like that, as soon as you have the coefficients, which are functions of time, you can just evaluate at any random point you want. Okay? So you have solved the problem once and for all. And it's okay to go to higher and higher degrees to ensure that you have something that has converged. What you should really never do, in papers at least, is solve it for degree 5 and that's it. Okay? Because then, you don't know if it has converged. Maybe you needed to go to degree 6 or 7, right? So you have to just test for that. And of course, another very good idea is as soon as you have done it, perhaps then you must, run 10 or 20 simulations at random points and compare the prediction of the polynomial chaos surrogate with the actual model. Okay, so just pick a couple of x's and compare the two responses. So they should match if polynomial chaos has converged. All right, so don't trust just the math. It's always just better to, set some samples aside for validating. What else? Okay, so I have 0 time for the handout, but next time I will only talk about this dynamical system and nothing else. Okay, so next time we will spend at least 30 minutes constructing polynomials and solving this dynamical system. And maybe I will include as an extra exercise in the handout one more dynamical system. Okay? But it's extremely important because this is a useful skill to have if you ever have to propagate uncertainties through a dynamical system. Now, if you don't, okay, it's fine. Okay? You will learn something new. All right? Any questions? Yes?
Why do you use the LHS?
Where do I use what?
Why did you use LHS approximation?
Oh, the Latin hypercube instead of the Monte Carlo? Because I don't know the right answer, and I have to compare to something. I want to compare the polynomial chaos approximation to something, and because I don't know the truth, I constructed an approximation using Latin hypercubes.
How do you know the Latin high
Has converged?
Yes, and the LHS is better than the PC.
I do not know that. I do not know that. I know that 10,000 Latin hypercube samples for this problem are more than enough. That's what I know. Why? Because I have solved this like 1,000 times. at some point I should have done an analysis, right?
So you assume LHS is the correct solution?
Yes, here, yes. Yes. So typically when you develop, if your research is on coming up with uncertain propagation techniques, that's how you would compare with a Monte Carlo estimate with a lot of samples, because this is sometimes the only thing you can do, right? But in a real problem, you don't have the solid line. You just have the polynomial approximation. All right?